Hi everyone. Today we are excited to introduce our project SafeMine AI. And the first is important to understand the context of core mining operation, which is high risk, zero tolerance. So based on this high-risk nature, China has a unified national safety regulations, and all the operation procedure must comply with this 700 of provisions in total. And this is a set-specific operation procedure. As you can see in the catalog, it's a really large document. And once the mines plans to a task, they must write this to instruct their operation. So all of the instruction must follow the safety regulations requirement. And this compliance report just show like what's look like. And to make it clear, we show it in 3 parts. The first part is a original sentence from the operation procedure, which means that the exact instructions that written by the drafter in the document. And then it will show the corresponding safety regulations requirement and check it against the operation procedure statement and make some analysis. In this example, the missing requirement is the personnel limits for the repair shift. And based on the analysis, it will return a final conclusion, which is non-compliant here. So I just want you to know the actual compliance checking is comparing the safety regulation requirement with the operation procedures actually state. And what's surprising is that in the real practice, this work is done manually. So to automate this process, the first thing we naturally wonder is, what if just ask GPT to do it? So we run a naive test. We take operation procedure with the national safety regulations and put them into a single prompt and ask GPT to check the compliance. We first use the whole operation procedure and GPT fails. Then we try narrowing the single chapter, and surprisingly, it works well on these small pieces. And as soon as the scope expanded to the multi-chapter, the GPT begins to fall in again. So from our test, we find an important issue is that the failure arises because one operation sentence can map to regulation conditions spread across different chapters. And this problem also appeared in the previous work. A recent paper used an OG RAG to handle this issue, so we test the same idea in our domain. And the paper highlights that the traditional RAG can't retrieve a full rule when these conditions are scattered. Inspired by the prior work, we'd like to introduce a data structure which we reorganize our safety regulation in that schema, which is ontology-grounded hypergraph. Okay, let's break it down. Here, the hypergraph helps us answer a simple question: what information element exists inside a safety regulation? By looking at the single hypergraph, we can see the rule broken down in its core components: the working phase, 300 meters, scope, and the personnel limits. So instead of treating the rule as one long sentence, hypergraph reorganize it in a set of clarity defined elements.
Next, with ontology, we define how these elements depend on each other. For example, if we have the zone type like the coal mining, and we can attach things like the limit scope or personal limits. Then this is why we need the ontology. It can let the system to reconstruct the rule which can form in the similar form to the operation procedure, in enabling the accurate retrieval. Then to show more clarity, during the retrieval we let the structure safety regulation to flatten in the form in this one, and this will be the foundation of our matching for the compliance part. Here is a whole pre-processing step, which we convert the raw national safety regulations to the structure safety regulation schema. Then we will now convert to the next part, which is the design of our SafeMine AI. Let's remember what we have done for the naive approach. We send out the thing to the GPT and it failed. Then this pre-processed safety regulation field becomes the first module of our SafeMine AI. With the regulation field ready, we'll continue to the actual input with the operation procedure. Then to process the input, we read it to the class level chunks and embed them. Then the system computes the top K first most similar evidence chunks for each rule, just for this one step forward. This becomes the second module of our SafeMine AI. Then, since we have the top K evidence trunk, we can let it to reason about our compliance. Once we have this, and finally, we put out the top key evidence trunk with the single prompt with GPT, and the agent produces the final compliance checking result and output to the users, which is the full architecture of our SafeMine AI. And the last part. Now we will come to the evaluation part. Under the same test conditions, SafeMine AI succeeds in nearly every cases. This chart visualizes the same trend cumulatively. As the document becomes longer, the naive GPT approach drops sharply in accuracy, while SafeMine AI remains consistently reliable. Since ontology building is expert and slow, we could only structure a small subset of rules. As a result, the system's accuracy drops. The whole document collapses onto just a few rules, increasing the noise in the top K. Looking forward, SafeMine AI will continue evolving towards stronger safety, smarter retrieval, and real-world deployment.
Thank you.